Good morning, everybody, and happy Friday, and welcome to the Informatics Institute PowerTalks seminar series. And I'm very happy to introduce today's speaker, Dr. Fabricio Kury. He's a clinical data strategist. He's a physician and lifelong computer programmer. He's devoted his career to using healthcare data analytics, and powers informatics to improve healthcare. Most recently, he has been clinical data strategist at the Mount Sinai Health System. And before that, he was senior manager at Regeneron Pharmaceuticals. And also before that, chief data officer at SAMI. He was a postdoctoral research scientist at Columbia University, working with our own Jim Semino, who unfortunately, I'm not sure he can join us today because they're having spring break. And anyway, he has many papers to his name, using data to improve healthcare and how to learn more from the data, and many volunteer efforts with renowned informatics organizations. Let's give a warm welcome to Dr. Fabricio Kury. His title of his talk is Current Practices and Frontiers in Role-Based Electronic Phenotyping.
Thank you very much, Amy. Good morning, everyone. I hope you can hear me well. Thank you for attending this talk in the PowerTalks series by the Informatics Institute of the University of Alabama Medical School. My name, as Amy said, is Fabricio Kury, and I personally thank you for attending my talk today. And thanks for the Informatics Institute for hosting the series, creating the space for this dialogue. I have worked first as a postdoc researcher, then as an industry employee in biomedical informatics for almost 8 years now. For the majority of this time, I have been involved hands-on doing the activity that is the topic of this presentation, which is electronic phenotyping, or just phenotyping for short. In this presentation, I wish to bring you a grounded view of phenotyping. I talk about the practice and try to connect to the science. And I lay a bit of opinion on top of it as well. I will talk about what phenotyping is, how it's done, some things that are difficult about it, and some points in need of scientific work. Much has been said about what phenotyping is. Let me give you a quick description in case you are new to the field. If you are coming to this presentation from a clinical research perspective, when you perform an observational study with medical data, phenotyping is what produced the patients and their covariates for your study. Say you're running a regression model. If you received a spreadsheet with the data that the model needs, phenotyping produced that spreadsheet. If you manipulated patient data yourself to produce that spreadsheet, you phenotyped yourself, perhaps even without knowing the term, which was my case too when I first phenotyped. The name phenotyping comes from biology. In biology, we know the genotype is the genetic code. The phenotype is how the genotype manifests itself to the outside world. The idea is that you can observe the phenotype and try to detect the genotype. In electronic phenotyping, it's similar. The phenotype is what you see on the medical data due to something having happened to the patient. Electronic phenotyping, or just phenotyping, remains done mostly for research purposes. But there are other use cases which have been growing. I have personally seen a provider institution using phenotyping as part of internal quality improvement work. I have also seen a payer institution using phenotyping to study care patterns and their costs. Whenever you are processing patient data according to a medical perspective, you're phenotyping. Phenotyping is a tool. Here I show an overview of the bigger picture around phenotyping. This slide represents how the information typically travels in this context. From the clinical event in the physical world all the way to the Excel spreadsheet that was used to run the regression model in the observational study. You have something that happened to the patient. I am calling it here the true clinical event. That event is unattainable to us. Something happened to the patient, he or she received healthcare. The process generated many records across many devices and systems, patient monitors, medical machines, gadgets, paper charts that later get digitized, EHRs, billing systems, pharmacy systems, laboratory systems, home care systems, emergency dispatch systems, and many others. Unlike in a traditional clinical trial, where you can collect data for your study, in phenotyping or in observational research, all you have are the data records that the clinical event left behind when it happened. We don't have access to the clinical event itself. Our task is to use data to make accurate statements about what really happened to the patient. From their source systems, the data gets converted multiple times in procedures that I am putting under the umbrella of extract, transform, and load operations, until it generally arrives at a data warehouse. The data warehouse is the powerful database in charge of serving the large-scale demanding queries of phenotyping. But if the data is not big, maybe you have some CSV files and you process them locally on your laptop. That also happens. So to restate, in phenotyping, we read patient data and identify patients and covariates for a study. Say you want to run a regression model, phenotyping gives you the patients and their covariates. If you want to run, for example, machine learning, phenotyping can provide you the samples and features, or in some cases, be the gold or silver standard for training the model. Let's look at a phenotype. This example was loosely picked from today's clinical literature. This is from weeks ago, March 18th. Let's look at who the researchers studied. The researchers investigated older adults with low-grade papillary stage TA non-muscle invasive bladder cancer. This entire sentence is what I'm calling the clinical event. Others would call it eligibility criteria. I am talking about the medical definition of the study subject. The phenotype tries to recognize that definition, that eligibility criteria, from the data trails it left behind. Here in this study, the phenotype uses diagnosis from a database called SEER, and the treatments and costs came from Medicare fee-for-service claims. This flowchart is the phenotype of the paper. Notice that it includes things that sound strange from the medical perspective. Why? Why do they exclude beneficiaries covered by Medicare Part C, which is Healthcare Maintenance Organization, HMO? This filter cost them 41% of the cohort. That's a lot. What does this restriction have to do with bladder cancer patients? This restriction is to address a data issue. Any period a beneficiary spends under Part C, under HMO, cannot possibly have any claim in it. The reason is because Medicare under Part C does not pay for services or items individually. That's the very point of the program. So providers don't bill Medicare for individual items. So data points such as diagnosis and procedure codes from claims, they may not have even been created at all. So what you normally do is you just exclude the whole patient from the study. The phenotype is in charge of addressing data issues. The eligibility criteria are not. The eligibility criteria represent the medical domain. The phenotype represents the data domain. Another example, also very recent, March 16th, also from JAMA Network Open. The fee-for-service filter was used just like the previous example. The distinction between eligibility criteria and phenotype is not sharp. For example, in both studies, they limited themselves to patients 65 years or older. Actually, in the prior study, they require 66 years. This is because they needed the patient to have had at least a full year of enrollment in fee-for-service Medicare before the patient is allowed to enter the study. This is called a washout period. If these two studies were not based in Medicare claims, maybe they would use a different age range. Maybe they would at least use a 65 years as the cutoff instead of 66 years, just maybe. The washout period that I mentioned is a minimum required period of enrollment before entry in the study. It serves to increase the probability that if the patient has a condition, you will have had enough time to get to see it. Remember, these are billing claims. You don't have access to the EHR. You only see ICD codes or CPT procedure codes or any data point at all when the patient receives healthcare and the providers bill Medicare for the care. You get to see that bill, that claim. That bill is your only window into what happened to the patient in this study. Medicare claims remain an unparalleled resource for studying, particularly the US elderly population. But they also represent a shrinking percentage of the total US elderly. If this trend continues, which is the explicit goal of CMS, researchers will need even more to look for alternative data sources. A different data set would change the rules in the flowcharts that I showed. It would change the phenotype. Maybe the age range would change, maybe not. But surely, if you had a different data set, you would stop excluding patients just because they had been enrolled in Part C at some point in their medical history. What would not change, however, are the eligibility criteria. The fact that these studies are about older adults with trauma and the low-grade papillary stage TA non-muscle invasive bladder cancer. My point is this: phenotypes address data matters. Eligibility criteria do not. The phenotype abstracts data matters away. The eligibility criteria are only concerned with the medical perspective. The eligibility criteria are determined by your research question. Your phenotype is determined by your data set. Phenotypes address data matters. Eligibility criteria do not. Machine learning has been studied extensively for phenotyping. However, rule-based phenotyping remains the majority of the cases where phenotyping is employed as a method rather than being studied itself. Rule-based phenotyping means someone has to know what to look for and how the data is supposed to look like and manually write down the rules, the algorithm. Personally, I think this term, rule-based phenotyping, can be sometimes misleading because machine learning can be used to generate rules for a phenotype, including human-readable rules. I like the terms hypothesis-first phenotyping versus data-first phenotyping. Hypothesis first starts from medical knowledge and the knowledge about how the data is supposed to look like and manually models a cohort. Data first starts from the data and uses algorithms to derive models from it. And let's add the eligibility criteria, which start from the medical knowledge and model a cohort in clinical terms. So let's say you are looking for prostate cancer patients and your data set does not have any diagnosis code at all. And then you decide to accept prostatectomy with adjuvant chemical castration, which is a treatment for prostate cancer, as a surrogate for the record of the diagnosis itself. That would be a change to the phenotype. You still want patients with prostate cancer. You are just when you're going to evaluate the phenotype, your gold standard is still going to be prostate cancer. You are just finding that those prostate cancer patients via a surrogate treatment pattern. Maybe that's because you don't have a diagnosis at all. Maybe that's because you don't trust your ICD codes. Truth is, ICD codes are surrogates as well. They are not the clinical event. Some patients will have the ICD code and not the cancer. Some patients will have the cancer and not the ICD code. So let me pause so I can make an analogy. The analogy is about what is the task in phenotyping. Perhaps you have heard about the allegory of the cave of Plato. It is a fictitious story from Plato that describes a philosophical idea. It goes like this. Imagine prisoners held captive inside a cave their whole lives since birth. They cannot see the reality outside, but they can see its shadows cast into the cave. The philosopher, the allegory goes, is the prisoner who comes to understand that the shadows are not reality, even though they come from reality. By carefully analyzing the shadows, the philosopher deduces bits of truth about reality. So in my analogy, the philosopher is the person developing the phenotype itself, is the person developing the phenotype, or perhaps the phenotype itself. The task is to make reliable claims about reality from looking just at the data. Perhaps you have seen this joke or some version of it. They ask, can you just quickly pull this data for me? To which you think, sure, let me just select everything from this ideal and pristine table that you think exists. The comedy in this joke is because they are overly optimistic about the data representation. They don't know that the data points being requested need to be produced instead of simply retrieved. As the data model determines the algorithm, data representation determines the phenotype. Let's look at an example of a phenotype. Embedded in every phenotype is an assumption about the data representation. That is how the curly braces problem, if you have heard of it, gets addressed. Let's look at an example. This is a publicly available phenotype. This phenotype is for detecting depression. It was produced by the eMERGE network and published at phkb.org. This website, phkb.org, by the way, has a wealth of phenotypes that you can study. This phenotype requires what it calls granular longitudinal data. Each site has to produce a set of data tables and then use those tables to execute the phenotype logic. What this requirement is doing is imposing ICD codes for diagnosis, ICD or CPT codes for procedures, medications identified by their generic names, and the Personal Health Questionnaire 9, PHQ-9, is a survey that gives a number from 0 to 27, and the phenotype indeed expects you to have that number in structure form. This phenotype also requires this rule called 2-30-180. It's another example of a technique to maximize the correlation between the data and the clinical event. Sometimes data exists in the absence of the clinical event. For example, a diagnosis code may be added to a patient's record because he is being evaluated for the possibility of the disease. And then later the diagnosis gets ruled out. But the code is already there and it stays there. This happens a lot. To address such cases, this phenotype requires diagnosis to exist at least twice in different days, at least a month apart, but less than 6 months apart. The details vary, but this requirement of multiple instances of the same data point in different days is very common in phenotyping. What is oftentimes left unsaid, however, is what is the date of the diagnosis when you require the two records on different dates? Is the diagnosis considered on since the first date or only starting from the second date? This can vary. If the statistical analysis uses the date of the diagnosis somehow, which is oftentimes the case, and the phenotype specification did not define which date to pick, which is also oftentimes the case, then someone somewhere at some godforsaken line of code has to make a decision about it. And just like that, the phenotype logic can fluctuate without anyone paying attention. Once you have the granular longitudinal data tables, as this phenotype calls the input data, you can run its logic. The logic is this flowchart. Running a flowchart is not difficult. If you are writing code, you could write a function that executes this logic. Things can get a bit harder, however, when you have a lot of data. If you have 87 million patients, billions of records, you need to be mindful about how you're computing this. For starters, you can't query one patient at a time. You can't write a function that receives a patient ID and queries the database and runs the phenotype for that patient. A much more computationally efficient approach is to produce each decision point separately, but for all patients at once. These red letters, A, B, C, D, and so on, I have added myself to facilitate talking about this. Each letter is one decision point that can be computed separately. Then you just follow the flowchart. For example, to arrive at case type 1, you need a true or yes on C and a true on B. To arrive at a case type 2, you need a yes on D, a no on C, and a yes on B. In this notation here, this is Boolean algebra. Exclamation mark means not. Multiplication means and addition means or. Looking at these formulas helps me do a few things. First, I can anticipate the impact of missing data. For example, the procedure codes, H and I, do not influence cases, only potential cases. So the lack of procedure codes is going to make me miss potential cases, but not cases. Second, if I can separately build each letter, each decision as an independent SQL query, I can also use them as subqueries inside one big mother query that puts the entire phenotype together. The SQL server would then run the entire logic of the phenotype for me. I download to my laptop just the final results. If I am a bit lucky, the query optimizer will make good use of indexes, and the whole computation gets done using very efficient algorithms. Remember that phenotyping is essentially a search task. You have a data set, and you need to find a record satisfying a set of constraints. If your query runs fast, you can also run it repeatedly. You have more opportunity for iterating, testing, and debugging. Needless to say, the more critical the computational performance of the phenotype, needless to say, the larger the data set, the more critical the computational performance of the phenotype becomes. Some phenotypes can take days, if not more, to finish processing. I am not saying it is the case of this phenotype, but this is something that I think we needed to talk more about. Computational issues in phenotyping. Lastly here, notice that despite their best efforts, handling data missingness can still be left not completely clear. Each decision point only has a yes exit and a no exit. There is not a not available exit. In principle, if you don't know, for example, whether the patient took any medication because you don't have pharmacy or drug administration records at all, that means G here is NA, not available, or U in the tables here at the bottom left, not false. In principle, there is a difference between not knowing if something happened and knowing something didn't happen. If the phenotype requires a false in G and the G is NA, then the result of the computation is NA, not false. What is being left unsaid here, which is frequently the case, is that NA is frequently considered equal to false for phenotyping. Sometimes this can be a valid assumption, but sometimes not. The document defining these depression phenotypes makes no specific mention about this. At best, this phenotype is addressing data missingness indirectly, rather than directly and explicitly. Let's look at another phenotype. This one seeks to identify patients who didn't have glaucoma, then started taking steroid drugs and began presenting increased intraocular pressure, or were treated for a treatment pattern that looks like glaucoma. So what would be our Boolean expressions here? Follow the flowchart. Unlike in the previous example, here each classification into steroid responsive or steroid non-responsive can possibly come from 3 endpoints instead of just 1. All you have to do is use the OR operator, which in Boolean algebra is the addition. So we follow the chart. To be a steroid responder, you can get a yes in F, a no in D, and a yes in B, or a yes in E, a yes in D, and a yes in B, and so on. And the same thing for steroid non-responder. So let's pause to do something fun here. What would be the formula for neither case? Not steroid responder, not steroid non-responder either. Well, let's just take each formula, negate, and combine with AND. Neither N equals to not SR and not SNR. So what then? Well, now you can manipulate the formula using the laws of Boolean algebra. You can do that manually, but you can also just use a Boolean algebra calculator. There are so many on the internet. A Boolean algebra calculator should be able to simplify the equation. This is the result. In this case, the logic of the flowchart had a gap, not A. Not A is what causes the patient to arrive nowhere. So tell me, did you notice that when you first saw this flowchart? That decision point A only has one arrow coming out of it. The flowchart doesn't tell you what to do if the answer to A is no. This case here is a simple one, but other cases can be harder. The hardest is when you don't have a flowchart, just a list of criteria and cohorts. By looking at this, are you able to tell me if there are any gaps in this logic? The idea here is, if you can write your phenotype as a Boolean expression where each component is an independent decision point, you can do a few things. You can manipulate it algebraically. For example, derive a formula that defines the exact difference between two phenotypes. You can build a truth table and use it to find gaps. You can use the formulas to organize your SQL query according to the expressions, which makes it easier to understand. and you can test and debug each decision point separately. Now, I'm not saying this approach to phenotypes with Boolean algebra is a silver bullet, but it is an underexplored technique in phenotyping. When I implemented this phenotype, I came across a detail. The phenotype asks, increase in intraocular pressure, IOP, after start of treatment. The author probably had in mind something like this. Well, take the measurement from before the treatment, that's A, and then take the measurement from after the treatment, that's B, subtract A from B. If the number is greater than equal to 6, that means yes. But in reality, the data for each patient looks more like this. What's more, the numbers fluctuate. There is noise in the measurements. One measurement is 16 millimeters of mercury. Soon after, it's 17, then it's 15. If you cherry pick the records, you can relatively easily find a pair of IOP measurements giving a difference equal to or above 6. Moreover, some tests give errors and need to be filtered out. What we decided to do in this phenotype is to use instead the pre-treatment average versus any record within 6 months after the start of the steroid treatment. Let's keep raising the bar of complexity. Let's talk about clinical scores. Say you want to study patients with disseminated intravascular coagulation. Chances are you will want to know the patient's platelet count. You could also want to know the patient's age. These exemplify data elements that can be considered easy. Something not easy would be if you wanted the score by the International Society of Thrombosis and Hemostasis, the ISTH score. That is a much taller order. That means finding a set of records within some limited distance in time to each other, then applying the mathematical logic of the score. Notice that suddenly you have to answer a new question. What is the expiration date of each data element? Can I use yesterday's D-dimer level with today's platelet count? What if there is another platelet count yesterday? What about the diagnosis of an underlying disease associated with DIC? Does it need to be recent too? How recent? Truth is, each data element carries its own baggage of domain expertise. Phenotyping has to cover that. An even harder task still is when the result of the computation is your phenotype. Imagine your phenotype is patients with ISTH score above 4. Now what happens? Now you don't have an index date or index encounter. The index date is whenever you can find a plausible combination of data points that give an ISTH score above 4. Computationally, if a query like this has no reference point, this usually means many SQL joins. This can be a challenge for the server if each table being joined has billions of rows. I am talking here about the dreaded SQL query that never finishes. If you just frame phenotyping purely like a constraint satisfaction problem, which is how eligibility criteria are phrased in English, then a phenotype can have a search space too large to be scanned by the server. Between the eligibility criteria between the eligibility criteria and the phenotype, you may need to leverage expertise about the clinical event or about the data to narrow the search space or search it more efficiently. Otherwise, the query may be too long to be practical. In this case here, one shortcut could be, for example, to aggregate data points on a per day basis and compute the score daily. that would shrink the size of the computation, but would also cause bias. For example, in the case the records are crossing the midnight line, if you're computing things on a daily basis, you are missing whenever the records cross the midnight line. This is a computation issue. I feel we don't talk enough about computation issues in phenotyping. Computation barriers can lead to workarounds, which can lead to hidden bias. This is another example of a clinical score that I have implemented in the past, the AS-CVD Risk Estimator Plus by the American College of Cardiology. How many data points does it have? Or better, how many interdependent data points does it have? Such that if you have to find them within a limited time distance to each other, you can't use last week's blood pressure with this week's cholesterol. For each interdependent data point, your SQL query will very probably have at least one SQL join. The SQL join gives you all possible combination of records to which you apply your rule, your where clause, limiting how far from each other in time they are permitted to be. You keep piling those SQL joins and the computation can become prohibitive. This is an instance of a computational challenge. It is possible to work around computational challenges, but workarounds are risky. They can break or flex the logic of the phenotype, and you may not even realize it. This is a niche area that I think deserves more research work. Computational complexity can grow exponentially when data points are interdependent. If your query takes 4 hours, that's short enough for you to wait for it. But that query is going to be hard to test if you have to wait that much every time you make a change. If we are to substantially increase our phenotyping abilities, then we need to address computation. A flowchart like this probably will not fit into a single SQL query, the one on the bottom right. And it is risky to try to figure out adaptations that increase efficiency but don't impact the logic. You can try to compute things in separate parts, but if the data points are mutually interdependent, for example, if they need to be close to each other in time, then that may be actually impossible. To my knowledge, presently there is only one proposal to advance computability in phenotyping. I won't dive into it here, but this is the citation. What Callahan et al. Did was get rid of SQL. They used an object data store that is a NoSQL database. By keeping all data for each patient in one place, the NoSQL database makes all the difference in performance for running decision logic at the patient level. So now I wanted to very briefly talk about tools that are used in phenotyping. Each of these tools easily warrants an entire presentation. The Leaf was developed by the University of Washington. And the idea is that you have the domains of data on the left, and you can drag and drop them to the right to build a Boolean expression. In each component, you can define, for example, it's hard to read, but here it says at least one time of the procedure. You can define at least 2 times, 3 times, and so on. Atlas, on the other hand, was produced by the Odyssey community and has so much into it. But for the purposes of phenotyping, it is a more sophisticated tool than Leaf. Atlas allows you to produce more sophisticated logic and also allows you to build reusable concept sets, which doesn't happen in Leaf. But again, I don't have time to review these tools. I just wanted to take a minute to review what they cannot do. Here are a few things that neither of those tools can do. They can't compare values between two records, only dates. For example, if you want to say, please give me patients where the hemoglobin level is lower than the last available record of hemoglobin. That's not possible. You can define that you want things happening after or before each other, so you can compare the dates, but you can't compare the values. Also, layering of the logic can be limited. If you think in terms of Boolean expressions, at some point you realize that you can't freely add parentheses anywhere in your expression if you're using those tools. And also, you can't do math, such as take a number, calculate something, and use that result in your phenotype. In principle, only a Turing-complete programming language can promise you it will be able to express any computable phenotype whatsoever. A graphical user interface-based tool is most likely orders of magnitude below the expressive power of a Turing-complete programming language. So with that, let's wrap up. A phenotype is an algorithm that abstracts patients and covariates from the data records the medical event left behind. The job of a phenotype is to look at patient data and infer truths about the patient and the care delivered. Phenotypes address data issues, unlike eligibility criteria. Phenotyping requires you to know or to require a particular data representation. Boolean algebra can investigate a phenotype at conceptual level. Computational complexity can impart insidious bias on phenotypes and warrants for further research. The greatest computational complexity in rule-based phenotyping is usually when many data points are interdependent and part of the entry event. Novel database technologies can reduce computational complexity by orders of magnitude. And finally, open source tools can model the logic of most phenotypes, but still lack major features and cannot compete with the expressive power of a programming language. Thank you very much, and I am more than happy to take your questions.
Great presentation. You really highlight an important topic. I think I like your slide that you showed that said, "Hey, give me my data," and there's this, either exists a clean table or just you just click a button and you get the clean table. But that all these issues involved, so that we really have to take any research results coming from EHR data, perhaps with a grain of salt. And so I'm wondering. You've done a really good job of highlighting the current state of things. So do we just kind of accept it that this is the limitation that we get, and that those shadows on the cave wall, that might be all we have. So we have to be content with that while we also try to find other solutions. So kind of wondering where do you see things headed? And especially as we try to catch up with other industries that seem to not have all these limitations.
Mm-hmm. Thank you, Amy. That's a great question. So the direction electronic phenotyping is moving is definitely towards the expansion of the landscape of medical data. The idea is that you needn't be limited to Medicare claims or EHRs, but perhaps you can also reach for an app installed in the patient's smartphone, or perhaps the patient uses a gadget, a Fitbit, and it's producing data that you didn't have before. So you try to incorporate that as part of the available pool of data to make inferences about the patient.
Yeah.
In the context of Medicare Part C, to get back to the idea of the shrinking representativeness of Medicare claims, Medicare has been trying to make more data available. What they do is they try to ask the healthcare institutions to send them what they call encounter data, which is not the claim, but is a description of what happened to the patient. They are trying to expand that, but it's still nowhere like the claims.
Yeah, that's the the limitation of using data that's collected more for reimbursement and reporting than actual clinical practice. And I think that unless you dive deeply into the study, you don't know these limitations. Like the one you showed it early on that said that half the patients were excluded because they didn't have claims, so that all these HMO patients would be excluded. And so so unless you know that, you just think that, oh, well, this is now this new gold standard based on rigorous data and rigorous scientific analysis. So
absolutely. What I like to say is this: in phenotyping, or perhaps in data analysis in general, at least in the healthcare domain, the harder thing is to figure out that something is wrong. The easy thing is to hide an error. It takes work to even realize that something went wrong.
Yeah, if you can hide anything with fancy math, I guess. Everybody, feel free to ask questions. You can unmute yourself, or you can also chat your question if you'd like. And you know what? You don't know this unless you're doing what you've done, which is actually trying to do these things. And someone says, "Oh, give me the clean data on whatever, so I can make this really groundbreaking discovery." And you're like you said, that the individual analyst has to make these judgment calls, because we know the data the data aren't clean typically. So, I mean, are you seeing anybody who is maybe maybe doing a better job than other places? What are some practices that you could say, here's some best practices for trying to do it better with what we have now, without.
Absolutely.
Yeah.
So I will give two answers to this question. One, in conceptual terms, in terms of how should you envision the task of phenotyping, how should you organize it? There is the idea of building a concept set separately from the logic of the phenotype. And before all that, you should do a literature review to get a grasp of how the clinical event looks like and what data you can expect the clinical event to have produced. So to dive into that, I definitely recommend you check the forums of the Odyssey community, the ohdsi.org. I will put here in the chat. In just recently, last month, 2 months ago in February, they ran the Phenotype February, which was on each day they posted on the forum an entire phenotype from the initial clinical literature all the way to the finalized logic. That's a very good lesson on how to build a phenotype, and there are 28 of them because it's one per day. And then in technical terms, if you want to know what is the pinnacle of phenotyping capabilities, I suggest you look into the reference that I showed, which is the advanced cohort engine. I have no relationship with that paper or that study whatsoever. I just recognize the value of what they did. This is the reference. And as I said, what they do is get rid of SQL. They use an object data store, and that requires, of course, you to give up SQL language, the SQL queries, which means they invented a new programming language that you have to use. But if you follow the method, then you can achieve a computational efficiency that is orders of magnitude above. I'm talking a query that would last hours, lasts seconds, which can completely change your experience as phenotyping, because if you can run something quickly, then you can iterate, you can check, you can see the numbers and do it again.
Yeah, thanks. Any other questions out there? Just a general statement. What you're talking about here is more the hypothesis-driven cohort, and well, I'm kind of thinking, where does this fit in the landscape, including data-driven cohorts? What would you say to the big data scientist who says, "Oh, forget all this; it's too complicated. Just take all my data and feed it into my big, pattern recognition algorithm, and then that will tell you what the phenotype is. The big data will tell you." How does this all fit together? What would you say to that person?
I'm not sure I understand the question. Do you mean what would I say in terms of are the limitations that the challenges that such person would find? Is that your question?
Kind of like, these are ways to define cohorts. So if you had to go with, the role of hypothesis-driven versus just the data type of identifying phenotypes.
Sure. Machine learning is good when you don't know how to find what you're looking for, but you know it when you see it, which means you have a gold standard, and then you can derive the rules. However, when phenotype is being employed as a tool, it's usually the case that you are coming to the study because you want to study something. So you already know what you're looking for. So in practice, the overwhelming majority of the papers that employ phenotyping use rule-based, because they are also interested in connecting to other papers in the literature. So it may not be the best idea to have their phenotype be locally developed or trained in local data. That would mean the cohort may only exist locally, if you know what I mean. As I said, data-first phenotyping is still limited to research work. Now, I'm sure there are institutions that do machine learning on patient data internally, and we never hear about it. But I would imagine those are more like one-off projects and prone and subject to the availability of people, of staff at each institution. When you're talking about using phenotyping today, you are generally talking about rule-based phenotyping or hypothesis-first phenotyping, because hypothesis-first phenotyping has this explicit connection to the medical domain. Whereas data first, maybe if your algorithm is very clever, maybe you can come up with human readable interpretations of the model, but maybe not, it can be blurry. So that connection to the medical domain, I think, is the critical point here that makes rule-based phenotyping be the choice.
Okay, thanks. I appreciate your putting that into context, because I've heard people say, well, you're limited with rules-based because you have to build these small cohorts and you get sampling problems versus the data-driven where you can look at the whole thing. But you're right. If you already know what you're looking for and you have specific questions that you're answering, and you want to connect it to what's been done before and in the literature, so it's good to hear that having a good clinical question and clinical context and are still valuable. Sometimes we feel like the data is kind of taking over everything. So appreciate everybody staying around. We're kind of at the end of our time now. Are there any final last questions? And if not, if you can also contact Dr. Kury afterwards. And also this recording will be available if anybody wants to. So any final questions? Well, if not, thank you so much for giving this really great presentation. I feel like this is, especially the people, I know some of the people on the talk of great interest, and myself too, of trying to identify cohorts for research. All right, well, everybody, have a great weekend, and thanks for attending, and thanks to Dr. Kury for the presentation, and we'll hope to see you at the next PowerTalk seminar.
Thank you very much, Amy, and thanks to the Informatics Institute.
Yep, goodbye.
Goodbye.